Welcome one and all to Optimal Control and Reinforcement Learning, affectionately nicknamed OCRL. I did not invent that. That was an organic acronyming. So I'm Zach, and yeah. Let's see. So first off, just to like have a nice little sort of soft introduction to things and get us going. I want to kind of talk a little bit. Well, I guess first thing is who we are and all that good stuff, and who you're going to be, listening to and interacting with this semester. So I'm Zach. That's me at the first one there. And then this is a fairly large class. We have a whole bunch of help. Kevin Tracy is kind of the lead TA slash most experienced of the bunch. He's one of my PhD students, and this is his second time TAing the class in addition to taking it. So he's well seasoned at this point. Swami, who's co-advised by me and Zico, JJ, and Renal, who's here. I don't think anybody else is actually physically here. I think a couple of people are on Zoom. Oh, hey guys, sorry, I didn't see you back there. Okay, so JJ, Swami, and then Renal, and Kevin is on Zoom. So yeah, that's the team, and you will be, interacting lots with everybody, hopefully this semester. What else? So yeah, I wanted to kind of give a little bit of a, warm-up pitch for why this stuff is cool and why you might be interested in this topic, and maybe, hopefully why you showed up today. So what is optimal control for? Lots of things. One of the kind of earliest use cases, and actually where the subject was kind of originally born, was in the aerospace field early on for designing trajectories for launch vehicles, for rockets, and then later on for things like planning trajectories to the moon during the Apollo program, and today, how we fly to Mars. So like this is kind of how JPL calculates, all the the burns and the course corrections and maneuvers to fly from the Earth to Mars, say, like Mars 2020 there. If anyone's curious, the way this mostly gets done, this sort of, terms of art and the stuff will be, we actually will cover in the class. This is nonlinear trajectory optimization. And in particular, most of this kind of stuff is done with an algorithm called direct collocation, which we're going to do in the class. Other fun things that are kind of recent and cool. Why doesn't this work? It's very annoying. Okay. Everyone's probably seen this at this point. There was just a really, really awesome rendition of this yesterday. Did anybody watch the Falcon Heavy footage from like yesterday? Incredible. Yeah. So cool. Like the like was it like 4K footage of like so cool. You guys should all go check it out. It's incredible. The videos don't play super well via Zoom, unfortunately, but so you guys have all seen this, right? So this is like autonomous landing of the first stage of the Falcon 9 rocket on a barge in the middle of the ocean. This is what it actually looks like. They light the rocket, and like that all happens super quick, and then it touches down on this, pitching, rolling thing in the middle of the ocean. Incredibly cool. Does anyone know how this works? Does anyone check this out or seen this before? Yeah, so this is convex model predictive control. This was actually a like huge seminal result in our field about 10 years ago, around like 2013 or so, where a guy named Bechet Achikmashe, who's a professor at the University of Washington now, and another guy named Lars Blackmore, who's now the controls lead at SpaceX, developed this technique they called lossless convexification, which was this technique for turning this rocket soft landing problem, which is very much a nonlinear, non-convex problem, as you can imagine, into a convex version that you can solve online at real-time rates with guarantees on the convergence side. So that's kind of the secret sauce, but behind this, and also how the Mars power descent stuff works. Super cool stuff. And one of the major results, in the last 10 years in control. What else? Autonomous driving, another kind of hot area that I'm sure everybody's been kind of aware of for a while. Arguably here, the control per se is not the hard part. The hard part here is mostly the perception problem of like, just figuring out where all the other cars are and where obstacles and pedestrians and bicycles are, and trying to, inform the controller of where those things are so you don't hit them. But similarly here, this is most of this stuff is done with MPC, in particular, nonlinear MPC with a simplified dynamics model. So most of this is using what are called bicycle models or single track models, really, really simple models of the car dynamics, and you just kind of solve an MPC problem online. So that's fairly straightforward. There is sort of frontier research going on in here that our lab has done a little bit of work on. One sort of tweak here that's really fun and interesting that sort of becomes kind of interesting from the control perspective is how you reason about what other cars are going to do and what other drivers are going to do. So this becomes a game theoretic control problem now. And so we've done some work in our lab on game theoretic model predictive control, where you actually try to reason about how your control moves will influence other drivers around you. And this comes up, for example, in highway merging, where you have to nudge your way in between two cars where there isn't enough space. And you need to kind of reason about if you force your way in, the other drivers will probably make room for you, which we do all the time, right? But vanilla MPC, on this Tesla, doesn't do that right now. And this is the source of this famous frozen robot problem you may have heard of, where the car will just kind of slam on the brakes if there's not enough room to merge in, right? So there's still really interesting control problems here on the driving side of things. What else? Legged robots. This has obviously been, one of the super hot, cool things in the last, say, 5-10 years. So this is MIT Cheetah. There's many other examples of this, like Animal from ETH and Spot from Boston Dynamics, right? Lots of these guys. Basically, all of these robots are doing MPC again, with some really interesting and clever model simplifications for the dynamics, so that you can basically treat this thing like a single rigid body in the MPC controller. You kind of do some fun tricks where you essentially assume the legs are massless, which is a reasonable approximation for these robots, actually, because all the motors are in the body. And so the legs are actually only maybe 10% of the body mass. And then you can do some fun things and get that MPC problem to solve at hundreds of hertz online. And then you can do fun, kick the robot demos that, mostly work. So that's pretty much all that legged stuff is doing this too. Also, yeah, super famous, awesome stuff that you guys have probably also seen, right? Boston Dynamics, Atlas doing parkour moves and, dancing videos, right? All this kind of stuff. Once again, this is MPC. In particular, these guys are doing some really state-of-the-art nonlinear MPC stuff where they're solving basically a whole body. So unlike the dog robot where you can sort of assume the legs are massless, here the legs are super beefy and have a lot of inertia, and you can't model those as massless anymore, right? And you have to reason about how the movements of the legs will sort of couple into the body. So here they're actually solving some version of a full body nonlinear MPC problem, reasoning over all the joints, right, and all this good stuff. And reasoning about contact with the ground, with the feet, and doing this all super fast online to pull this stuff off. I mean, this is basically, as good. This is the state of the art right now, I'd say, certainly for legged robots. It's super awesome stuff. So yeah, lots of MPC. I should mention, actually, the MPC stuff here is actually just doing the online tracking. So a lot of these motions are designed offline first, using mostly trajectory optimization techniques and things like this. And then sort of stitched together online to form these longer behaviors, and then those are tracked with nonlinear MPC. So these are some, these are all the cool things you can do. We're actually going to explicitly cover just about all of these topics in the class. So you'll at least get a taste of how all these things are done. And towards the end, we're going to do case studies on rocket landings, legged robots, driving, all this good stuff. So you'll actually have a fairly good idea by the end of the class how to do this kind of stuff. And also get a chance to do it yourself on some of the homework problems. And as part of the class project, you can sort of choose your own adventure and bite off one of these things and try to do it. Cool. Okay, so these are things that are kind of right at the frontier right now, the state of the art. So just to kind of maybe plant some seeds of thoughts of ideas for research stuff here, I would say here for us, right, in our lab, where this is kind of what we do all day, some of the kind of really big current challenges in the field, I would say one is with all that legged locomotion stuff, dealing with contact interactions with the environment. So this is both in legged locomotion and in manipulation in robotics. You end up with discontinuities in the dynamics, right? So you end up with like giant, spiky things that happen in your contact forces when your foot hits the ground and stuff like this. And you get non-smooth dynamics, which means you can no longer take nice gradients through things and do standard gradient-based optimization things, which make these problems super, super hard. So that's still a hard sort of, in spite of the recent successes with Boston Dynamics and MIT Cheetah and all these things, there's still some really hard problems there, and there's still kind of demons lurking. And we don't have I would say, a general theory of how to do this yet. There's lots of hacks behind all of these examples you're currently seeing that work sometimes better than others and also still break. Another one that's really big. So from my perspective, right, this class is called Optimal Control and Reinforcement Learning. The perspective is very much coming from optimal control, but I would argue that optimal control and RL are really the same thing. The difference is really more like style and philosophy, and whether you're coming from, say, engineering or computer science, but they're really the same thing. And the differences are kind of subtle and oftentimes, more about like notation and lingo than substance. So in this class, we're really going to try to give you the fundamentals coming from like the classical optimal control side, but the same math and same tools are just super applicable to the RL stuff. And there's really a very blurry continuum between these two. So we're going to kind of start with the real basic optimal control stuff. And towards the end of the class, we'll sort of dig into data-driven techniques and things that are kind of more from the RL side. But yeah, there's this real big divide between people who come from this classical engineering optimal control side of things and this more kind of like computer science-y reinforcement learning side of things. And there's good ideas on both sides, but right now there's a big gap between people who work on both sides. And I'd say like bridging this gap is currently a big deal. And I think one of the best things you can do if you want to be a researcher in this area is be super fluent in both sides. Because I think there's a huge intersection area there that's really underexplored. So if you can do both really well, there's lots of opportunities. Yeah, so along those lines, I think there's lots of room for making these reinforcement learning or more data-driven techniques more data efficient by kind of leveraging prior knowledge from kind of the optimal control side of things. Another one that's really big is trying to give safety guarantees, especially for uncertain nonlinear systems, so things where your model's not quite perfect, or you have uncertainty in the dynamics or in certain model parameters, or there's disturbances coming from the environment. Given that kind of stuff, can we still give safety guarantees? Can we still guarantee the car is not going to crash into pedestrian, right? This kind of thing. So these are really, really big deal, particularly in aerospace applications and driving where human lives are on the line. So these kind of safety guarantee questions are huge. And the last one that's kind of super interesting is dealing with other possibly not super friendly agents in the environment. So this is driving where you got to deal with other humans in particular is where this shows up, but kind of reasoning about what other humans maybe or other autonomous agents around you are going to do and how your actions can influence them. Cool. So these are kind of fun ideas, maybe to plant sort of project ideas in your head or future research directions that you might want to check out. Any questions about any of this stuff? No? Cool. Okay. And that doesn't work. So, okay, so then big picture, what are we doing here? Optimization-based control techniques. So I think there's a lot of kind of, classical, shall we say, baggage or connotations associated with optimal control. And I think in here, we're going to take a very broad view. And so basically the idea here is if you're anything where you're using optimization tools to do control is kind of what we're going to talk about in the class. So anything like kind of that fits that is fair game. And we're going to really focus on practical applications in robotics as opposed to theory. So we're not going to do like a lot of theorem proving in here. We're going to do a lot more like code it up and try it in simulation on, a quad rotor, this kind of thing, right? So super practical, and hopefully you can like take the stuff from the class and use it directly in your research and stuff like that. We're going to do lots of Jupyter notebooks in class that I will distribute to you guys. So you'll get lots of examples and hands-on kind of coding up of these things. There's going to be approximately 4 homeworks. There's sort of 4 real homeworks and 1 sort of fake homework that we're going to call homework 0. That's going to go out on Thursday this week. That's basically just bootstrapping all of the like tooling you need to do the homework. So it's like making sure you know how to use GitHub and how to, submit things, and a few like really kind of background learning the ropes, kind of things. It shouldn't take you more than like half an hour to do. It's not really a real homework. And then there'll be kind of 4 real ones. I should say on that one, everything in this class is in Julia. So I figured this is equal opportunity for both the MATLAB and Python haters. It's annoying for everybody. If you haven't used it before, it really looks and feels mostly like MATLAB. And it's super easy to pick up. If you know either Python or MATLAB, it shouldn't be any trouble. It's really, really easy. So that's what we're going to do all the like stuff in lecture in, and like all the homeworks will be in that. It uses Jupyter just like Python notebooks, so that's pretty straightforward. And then the last thing is we're gonna, at the end of it, there's gonna be a sort of semester-long course project, like a final project. There's no exams, and the idea here is just do something cool with stuff from the class. It's super open-ended, and I really want you guys to like use the tools in your research, or just something you think is cool. Just go for it, as long as it sort of fits that first bullet point that there's something optimization flavored in there. It's fair game. Any kind of RL thing you want to do, any kind of control thing you want to do on any kind of system, fair game. So on the first homework, there's going to be a sort of form a group. I highly recommend you do this with friends. If you really want to do it by yourself, that's allowed, but it'll be much more fun if you do this with a few friends. I would say max group size is 5, just to cap things. But yeah, 1 to 5, try to find some friends to do it with. If you're having a real hard time finding friends to do it with, maybe we can help do some matchmaking, but I'm gonna kind of leave it to you guys as part of homework 1 to find some friends to make groups. So on the first homework, there will be a question that was gonna force you to find a group and then come up with a topic. And basically from there, we'll kind of iterate. So I'll try to talk to every single group sort of in the week or 2 after that first assignment is due, try to help you dial in your project scope a little bit and hopefully point you towards some references and things like that. And what else? Yeah, and then as far as the homeworks will be coding assignments, GitHub, blah, blah, blah. Course project will be, there'll be like kind of a lightning talk because this class got so big that we can't have much longer talks. So the last week of class, the last 2 lectures will be lightning talks from every group, super quick. And then there'll be a report like right up for that. And the idea for the report is to make it look like roughly like an IEEE conference paper. So it's like in the style of like an ICRA or IROS paper. So it's 6 pages, not too long. And the hope is that, most of your grad students here, that you can kind of use this as a forcing function to hopefully get a conference paper out and hopefully do something, useful for your research, and kind of hopefully, turn it into a real thing that you can submit somewhere. Any questions about any of that stuff? No, I'm good. Okay. And then some more logisticsy things. Lectures in here, you're here, so you figured that out. I'm also going to live stream on Zoom, which I'm doing right now. And I'm also going to record everything and post them on YouTube. I did this last year as well, so you can see all the videos from last year on YouTube. There's a YouTube channel, it's public. So I'm going to do that again. And then everything I write down and any slides I show and any code demos that I do in class, so like Jupyter notebooks, slides, and my written notes will all get posted on GitHub after every lecture. So you'll have like recordings, everything I can possibly give you is going to be posted online. So if you have to miss class, no big deal. If you have to like do this asynchronously because you're double booked with another class, which I know a few people are, that's fine. Try to make it as easy as possible for everybody to get something out of this and have a good time. Let's see, we're gonna use Piazza for like general questions and kind of interaction and stuff. I used to use Slack, but then the class got too big for Slack. So now it's Piazza. Homework, we're gonna post homework in a GitHub repo that you can clone and then do your thing. And then we're going to collect submissions through Gradescope. So there's going to be basically like dump a PDF out of your Jupyter notebook and upload it to Gradescope. And then office hours, we're going to ask you guys to fill out like a scheduling poll. Is that up yet?
Not yet.
Okay. Okay, so that'll get posted like tonight, and we'll post the link on Piazza, basically like a little kind of when to meet or whatever, to try to figure out what the best times are to get to the most people, that kind of thing. So additional logistics that aren't on here, which we're going to try new this year. We're going to try to do also a recitation section on Fridays. So it'll just be every Friday. We'll schedule that also based on a poll that I'll show in a sec. And it's totally optional, but the idea is it'll be sort of like Kevin's going to kind of go over some maybe tricky stuff from the lectures that week, extra help, extra, basically office hours time as well. So if there's anything that wasn't super clear, or you need to catch up, or you weren't in class and you had to watch the YouTube videos, and you had questions or whatever, you can always hit up the recitation section on Fridays also, and get sort of a second go around of any kind of tricky bits. And those will get recorded and posted as well. Recitation, what else? Oh, and the last thing is we're going to try to do also new this year, little quizzes every week. So these will be like 5 multiple choice questions that'll count towards your participation grade. It's gonna be a small chunk of your grade. But yeah, just to kind of like make sure you're up to pace with like the lecture. So if you're not here and you're doing it asynchronously, it's sort of force you to actually watch the videos every week kind of thing, and keep up with stuff. And just to kind of make sure you're getting like the basics out of what you should be getting, and that, kind of things are clicking. So that's what that's for. And it should take you like 10 minutes. It's gonna be a really short thing. Okay, I think that's that. Any questions on any of this stuff? Yeah.
So those quizzes, will they be like submitted online?
Yeah, it's gonna be on Canvas. It'll be like a few, like 5 multiple choice questions that you should be able to like just click through in like 2 minutes or whatever and submit. So it should be like very, very minimal effort and super quick. And I think we'll post them like on Thursday or Friday, and they'll be due like, the next Tuesday or something like that. Okay, anybody else? All right, so a couple things that will, you don't have to do this right this second, but we're gonna, there's a course survey that is also posted on Canvas and Piazza that asks kind of basic questions about your background and stuff to help me sort of calibrate some stuff. And also has a question in there for time blocks you're available on Friday for the recitation. So we're gonna try to schedule that at the time that's most available for everybody. There's the Piazza link. You can grab it now, or you can grab it from the slides later. I think that's that. Okay, cool. So then I think what we'll do real quick, also just to make things super clear and stuff, we'll go like look at some of this stuff real quick. This is Canvas. We're not really going to use Canvas too much. This is just going to be for kind of grade stuff. But otherwise, I'm not really going to post anything on here. So the front page of the Canvas site, though, has links to all the stuff. And then the Piazza front page also has links to all the stuff. So you can get on any one of these. You will have links to all of the other things. So this has like links to the GitHub, where all the sort of lecture notes are going to be posted. The stuff from last year is up there as well in an archived repo, so you can look back there too. What else? YouTube channel where all the videos are posted. What else is important? Oh, syllabus would be good to go through. Okay, so here's the syllabus. We'll just take a quick perusal of this. And I'll keep updating this as we go through the semester. So the main thing that we should take a quick look at, so here's grading. Quiz grades will get kind of stuffed in here. And this is basically for me to have wiggle room to sort of boost you over the edge of a letter grade if there's kind of a discrepancy, but it's basically going to be, half project, half homework with a little wiggle room. And yeah, so homeworks, there's 4 of them. So those are 10% each towards your final grade. Late homework, we're going to give you a budget of 6 late days. I'm generally pretty lenient about this stuff, but be reasonable. Don't make me have to like chase you down with this kind of stuff. What else? Here's kind of tentative topics and schedule. This will probably get, squished a little bit here and there. Here's today. So we're going to start out doing basically a crash course in dynamics first, and sort of how to discretize dynamics for the kind of computer sciencey people in here who've never taken a dynamics class or an ODE course or anything like that. Then we're going to kind of, so this is kind of everything you need to know about dynamics in a couple of lectures. So we'll talk about like stability and this kind of stuff. And then we're going to spend a few lectures doing just optimization, sort of straight up optimization, no optimal control yet. So this is just to kind of get you enough background in optimization. Again, sort of 3-lecture crash course, enough to be dangerous. So you know what we're talking about when we start using that stuff to do optimal control. And then from there, we'll get into kind of the optimal control stuff, kind of bootstrap on that. So we'll spend a good amount of time on LQR, which is the crown jewel of control theory, it's been called, right? It's one of the kind of the main super great things. It's like maybe the only control problem where we actually can basically get a closed form solution, which is why we try to approximate everything else as an LQR problem, which is why it's super useful. We'll talk about dynamic programming, convex model predictive control. So this is rocket soft landing, for example. Nonlinear trajectory optimization and a couple different algorithms for doing that. So iterative LQR, which maybe some of you guys have heard of, and then direct collocation, which is one of the other big sort of algorithms for that kind of stuff. Some extensions to those methods. And then this one is a personal, like, I don't know, passion of mine. We're going to talk about how to handle attitude. So this is like the SO3 group, or, things like, free floating base, flying things, underwater things where you have large rotations. There are sort of good ways and bad ways to do this. And unfortunately, way too many people use bad ways, like Euler angles, which are bad. They're bad for you. You shouldn't use them. So we're going to tell you how to do it the right way. This is spring break. Then, some quad rotor stuff. And then we're going to start talking about contact dynamics. So this is like legged robot stuff, how we, do Boston Dynamics kind of things at a very high level. We're actually going to cover, like, I'm going to you're going to do like a biped on the homework. So we'll do some of that stuff. And my iPad just crapped out. Then we'll get into a little bit of this kind of sort of, getting away from the stock optimal control stuff a little bit. So some stuff on data-driven methods, some techniques called iterative learning control that are really powerful, but have kind of been forgotten in the last 10 years with the deep everything hype, but are extremely effective. And honestly, like, probably more people should know about this. So I'm going to teach you about it. Some stuff on stochastic problems and the so-called LQG problem, which is where Kalman filters come from, robust control kind of stuff, some random hodgepodge of RL topics, which Swami might help us out with. Then this one, which is kind of a catch-all for a bunch of stuff that doesn't really fit anywhere else, but I want to cover, which is practical tips and tricks, and then like a tour of the history of this field. And then we're going to do a bunch of case studies towards the end. So the rocket landing stuff, driving stuff, and then legged robot kind of walking stuff. And then the last week, the last 2 lectures will be these lightning talks. And basically the exact timing there will depend on exactly how many groups you end up with and all that kind of stuff. So I think that's it for the syllabus. Any questions about any of that stuff? It's the main stuff. There's project guidelines in here. So if you're curious about that, that's kind of in here. So take a look at this. I think that's it for logistical things. Anyone have any general questions about the class, about how we're going to run things, about any logistical stuff before we like actually get into real stuff? And also, as part of getting into real stuff, I need to make my stupid iPad work again. Is that going to work? Nope. Of course not. Of course it's not going to work. Why would that work? Oh, by the way, Zoom people, I can't really look at the chat while I'm doing the screen share stuff. So feel free to just unmute yourself and speak up. That's definitely the best way to do this. And so someone asked, can we audit the course? Yes, you can audit the course. That's no problem. Okay, this looks like it might work again. Sorry for the Wi-Fi spottiness it's always a problem. Okay, yeah, maybe. Hate this part. The awkward waiting for technology to cooperate part is the worst. Yeah. Oh yeah, what's up?
So yeah, about
One is about like homework. So some people group the stuff that you track of, like, say, contributions of individuals, members, or to be like, is it great for everyone?
Yeah, so on the final project specifically, yeah. So I think the general idea is that, yeah, you'll all kind of get the same grade. What I have done in the past to try to, which I generally don't advertise, but what I'll do is send a little like peer review survey out, so that if there's a member of the group that isn't sort of pulling their weight, or there's some situation like that. So first of all, if there's a situation like that, come talk to me early. And hopefully we can deal with it before we get to that point. But if, yeah, we'll do like a little peer review thing at the end to sort of like hopefully account for that eventuality. But hopefully, yeah, we can deal with that sort of thing. The idea is work with your friends, work with people you like, and hopefully it's not a problem unless someone gets sick or something like that, right? All right. And yeah, if it is a problem, the best thing is come talk to me early and have like a tight feedback loop on everything. Anybody else? Anything? Okay. If we're good, then let's get into it. So as a general rule, yeah, feel free to just like yell at me, because I'm going to be like staring at screens and stuff and looking down a lot, and I probably won't see you raise your hand. And I also can't see the Zoom chat very easily. So just make noise and like get my attention. And yeah, definitely interrupt and ask questions. It's free. I'm here for you guys. Like there's no other reason for me to be here. So like, you know, definitely speak up. Okay, cool. So we're going to talk about continuous time dynamics. And so, yeah, again, the goal here is to like mostly for people who haven't seen this stuff before, give you enough ammunition to like be dangerous. But it's not a general course in this stuff. So the most general / generic form of this stuff for a smooth system. So sort of a continuous time dynamical system looks like this. So this is a controlled system, and we've got a few things to note here. So this F guy is called dynamics. X is called the state. And we usually assume this guy's a vector in Rn, although that's frequently not the case in robotics. And we'll talk a little bit about when that you really have to think about that. But usually we assume that's just a vector in Rn. And then this U guy is the control input, or just input. And this is a vector in Rm. So these, in general, right, the state dimension and the input dimension are different sizes. What else? Okay, so for a mechanical system, like a robot, for instance, we have this state vector X is the idea here, right? Is this state vector just has enough stuff in it to describe everything you need to know about the system in general, right? So inside here, generally for a mechanical system, there's what we call the configuration, which is basically the position and or orientation of everything. So for a, for like a humanoid robot, this would be probably like the position and orientation of like the trunk, and then all the joint angles for all the limbs, right? It's everything you need to write down where that thing is in the world. And then, so that's configuration, which we use the letter Q for, and then the velocities V. So this guy Q is configuration. And this is importantly, this Q is not always a vector. We'll see examples of that. In a minute. So that's not always a vector. And then this guy is the velocity, which is always a vector, it turns out. Okay, any questions about that? Cool. So now we will talk about everyone's favorite toy nonlinear system, the pendulum. And sorry? Let's see, what's a good, you can take derivatives of it. So an example of maybe it's better to have a counterexample. An example of a non-smooth system would be one with impacts. So like if I do this, I have a legged robot and I have like footsteps happening where my feet are bashing into the ground. I have discontinuities there where there's a jump in the velocity, right? It's like moving, and then like all of a sudden 0, right? When it whacks into the ground. That's an example of a non-smooth system. So anything that moves sort of continuously and you can differentiate the trajectories, right? That's what we mean by smooth. Does that make sense? Yeah. Cool. Yeah, it's like a stand-in for differentiable, if that like, hopefully that makes sense. Okay, pendulum. So we'll draw the cartoon picture, and this I'm sure everyone has seen before, so we won't spend too much time on this. It's just an example to illustrate. Yeah. Yeah, let's see. Can we do, sorry, is that better? Okay, cool. Yeah, no, I can't see it. Oh, okay. This is gonna be awkward. I don't know. We'll figure it out. Yeah. Yeah, we could try that. It's just, then I have to scroll a lot, which is really annoying. But if that works for you guys, we can give it a shot. Is that better? You guys like that better? Okay, cool. We'll try that. Okay. So what do we have here? So this guy has mass M, length L, angle theta here. And we've all seen this before, so I'm just going to write down the equations of motion. So this is ml squared theta double dot plus mgl sine theta. And here we're going to have a control input because it's a control class. So we're going to assume you can apply a torque at the joint. So that's tau. And so for us, that tau is u. This is just the torque at the top. Okay. So to sort of like make some of this clear from like our discussion about, smooth dynamics and all that, and this like more abstract thing with a, configuration and all this stuff. So here, what is the configuration Q? Beta, it's that angle, right? And then you can choose different things here, but we're going to use theta dot for our velocity. So in this particular case, V equals Q dot. That is not always true, though. In fact, it's often not true. So we're going to kind of make that sort of Q dot versus V distinction pretty clear. What else? Okay, so those are the Q's and the V's. So then the state vector X is equal to theta dot. And we can kind of write the dynamics down in the form that sort of generic f of x u form, like so. So this, we just stack everything up kind of the expected way, and we just kind of solve this for theta double dot. So we get this inside here. Right, so this guy is our f of x u. Okay, so here's a fun question. Is the state here in so let's go with the configuration. Is the configuration here, is this thing in Rn? Is this a vector in Rn? The state or configuration of this guy? What do we think? Show of hands for yes. Anyone think no? Who thinks no? Yeah. Do you have a reason why you think it's not?
Yeah, it's like a circle.
Yeah, exactly. Okay, this is right on. So this kind of all this weird stuff about things are not in vector spaces. This is trivial example. The pendulum is not in a vector space, right? So the theta there is not on the real line. It wraps around on itself, right? So the what's called the configuration manifold is actually the circle, which we call S1. So not already, even for like something really simple, we're not in Rn. Oh. So this guy, Q, is in S1, which is the circle. We're not going to do a ton of this kind of stuff. I'm just kind of like, I don't know, telling you these things for fun, because these are the sorts of things that often don't get covered in like intro courses on this stuff. And does anyone know what the velocities are then? Anyone have any thoughts? Is the velocity a vector? Kind of already gave this away. So the velocities are always a vector. And the reason is, if I think about, the definition of like derivative in the most basic sense, it's like a tangent, right? So if the configuration's on the circle, velocity is always in that tangent plane to the circle. So that is R. That's just the vector space, right? So then the whole state lives in this manifold S1 cross R. So that cross notation, that's called a Cartesian product. What that means is for every element on S1, so every theta on the circle, there's a real line, tangent to it. So for every theta, there's a theta dot that goes with it, right? That's called a tangent bundle, if you're fancy. And does anyone know geometrically what that is? It's a cylinder, that's right. So the state space for the pendulum is not R2, it's the cylinder, which is kind of fun and actually does make a difference sometimes. So I don't know, these are fun things. So as just like a fun one, does anyone know what the configuration manifold for a double pendulum is? It's a torus, right? You got two circles. You got a circle with a theta for the first link and a circle for theta for the second link. And so for every, circle you got another circle for the other link. So you put those together and you get a torus, right? A donut. Okay, fun facts. Getting distracted. Okay, so what else? Okay, so this is like the generic stuff, f of xu, most basic stuff. There's a bunch of now like more specialized forms of dynamics that we'll run into where there's special structure beyond that just generic f of xu that's useful for control. So the first one to talk about that comes up a lot, and there's a lot of control theory that's based on this, are so-called control affine systems. So these are still nonlinear, but they're linear in U. So they look like this. You have, we'll call it F naught of X. So this is just a function of the state. And then the control enters like this. So we have some matrix that can be a function of X times U. So in the lingo, this F naught guy is called the drift term. And then this B guy is called the input Jacobian. So control affine, it's affine in U, right? It's U enters linearly via this B matrix. And then there's this extra drift term, so it's affine in U. Make sense? So these are actually surprisingly common. You might think this is like, not everything is like this, but basically, I think any smooth system you can actually write this way. And basically anything we care about in robotics, it can be written in this form. There's sort of a trivial trick for writing something in this form if it's not already in this form. Does anyone know what the trick is? And we'll do the pendulum example. If anyone knows, yeah, speak up if you know the trick. So here's the F naught for the pendulum. It's all the stuff that doesn't involve U. So there's your drift term, and then your B of X is a column matrix, because U is one-dimensional. And it just looks like that, right? It's the stuff that's multiplying U up here. We just kind of split that apart, right? Everyone cool with that? Yeah. All right. Okay, so next one. So that's control affine. Shows up a lot. And there's a lot of control theory based on this structure. So now we get into a little bit more specialized. This is really a robotics thing. So this is called manipulator dynamics. So here's what those look like. So this is a little bit more structure beyond just control F. So this is control affine, right? Obviously, but there's a little bit more going on top of that. So this M of Q matrix is called the mass matrix, or inertia tensor, or generalized inertia tensor if you want to be fancy. This C guy, there's a few different variations on how to write this down, but this is the way it's done in the dynamics toolbox we're going to use in Julia in the homeworks. So that's why I'm writing it this way. This is called the dynamic bias term. So this includes stuff like Coriolis terms and gravity, which sometimes you separate out in other, you might see books where there's a C and a G, and the C is the Coriolis terms and the G is the gravity or potential terms. And then again, the B is called input Jacobian, like before. Be a little careful because this gets overloaded. So this B here is a little different than the B that we wrote for control affine, right? Actually, this B is just a function of Q, not of X, right? And this B is smaller than this one. This B here is basically the bottom half of that B. So these get overloaded all the time. So be careful based on which version of this you're writing down. And then in general, on this whole topic of like, Q dot doesn't necessarily equal V. In general, you have something that looks like this. Q dot equals some linear function of V. And we call this the velocity kinematics. So this comes up in particular in this class. We'll see it when we talk about attitude dynamics. So when you have like a quadrotor, say, where the attitude is parameterized with a quaternion or a rotation matrix or Euler angles if you're sadistic, the mapping between omega, which is your angular velocity, and the attitude, which is the configuration, looks like this. There's some kinematic Jacobian matrix in there that maps omegas into Q dots for your Euler angles, quaternion, rotation matrix, whatever, right? So that's where this comes from. So this is pretty general. And then, yeah, you can turn if you have this form, you can turn it into our generic f of x u stuff like so. So the first line is trivial. It's just the kinematic stuff. And then the second line is I just solve that manipulator equation for V dot. So I get like minus M inverse times B U minus C. Cool. Okay, so back to our, trusty pendulum example. We've got, so if I want to write out in those manipulator blocks, the M of Q here for the pendulum is ML squared. The Coriolis term is GL sine theta. And then, why did you do this to me? Yeah, it didn't crap out entirely. Okay, cool. And then, yeah, the B matrix and the G matrix are both identities here. So cool. And then where does this manipulator thing show up? If you've taken any kind of robotics, class like KDC or whatever, you've seen this before, right? So this is quite general. So all mechanical systems can be written in this form. So basically any robot. Yep.
I think you got an extra negative sign. M inverse Q minus C. It'll be.
Yeah. Thanks. Cool. Okay, so all mechanical systems. Does anyone know why? What's energy? You're kind of on the right track.
Isn't this just the manipulation of the Lagrange equation?
This is exactly the Euler-Lagrange equation for a specific Lagrangian. So yeah, that's right. So what this is just this is just rewriting the Euler-Lagrange equation. With a particular form of Lagrangian, which is L equals 1/2 V transpose M of Q V minus your potential, which can be anything, right? So really, it's just assuming that your kinetic energy looks like that, where that M is your mass matrix, right? Which is true for any mechanical system, any kind of robot. Yep.
Are we accounting for the damping forces or non-linear forces in general, like?
So those show up on the right-hand side as additional forces. So in general, you'll have like another generalized force input F. So yeah, I should have probably written that. So this would be external forces. Yeah, so you can't write damping down in a Lagrangian, right? It's only the conservative stuff. So this is just the conservative stuff. And then, yeah, the stuff on the right-hand side of the equal sign is all the non-conservative forces. So that's control inputs and then anything else. So yeah, damping would show up in that F. Contact forces would show up in that F. Anything else? Yeah. Anybody else? Yeah.
Is that, what's the thing at the end of it?
That's the potential energy.
Oh, is that a U?
Yeah. Sorry. This is so let me add. This isn't like crucial for the class. It's just kind of like a background survey kind of thing. Sorry? They're not actually the same thing. So they're only the same in a Euclidean reference frame. They're only the same if you use Cartesian coordinates. So if you choose generalized coordinates that are not sort of, nice Cartesian coordinates for like a point particle. So for example, a robot where you choose to use a quaternion for the orientation and joint angles for the limbs, then this isn't quite F equals MA. So in the special case where you're in R3 with a point mass and it's a Cartesian, it is F equals MA, exactly. But yeah, in the general case, it's a lot more complicated. Yeah, the generalized coordinates thing is sort of the key thing, which are your Q's or your, yeah, you get it. Cool. Yeah, if anyone wants to show how to get the manipulator equation from that Lagrangian, bonus points. It's kind of fun and slightly non-trivial. You need to think about tensors to do it. Okay, cool. So that's manipulator dynamics, super useful in robotics. And then the other one that is sort of what we're all about in control, the sort of bread and butter stuff for control are linear systems. And these look like x dot equals a, and I'm going to put t's in here, ax plus bu. So it's linear in both x and u, and the matrices here that are the coefficients, the a and b, in general can be functions of time. And there's a few variations on the theme here. So it's called time invariant. if A of t equals some constant A and B of t equals some constant B, called time varying otherwise. There are some other variations that show up occasionally, like periodic, which shows up for like tracking, say, a walking gait that's periodic. So you can have that. That is a special case of time varying. There's some other versions of this, but these are the main kind of things to think about. And these are super, super important in control. Control theory is basically, this is the stuff we know how to solve in closed form, right? So we're going to spend a lot of time with these guys. And I would say, if you really, really want to, get into this subject in a deep way, highly, highly recommend taking a linear systems theory course, which here there's a course along these lines in ECE that you can take that covers sort of a lot of general theory about these kind of things and like, all the math that you need to like manipulate these things effectively. And then as a kind of note here, we very often approximate nonlinear systems with linear ones, right? These are the ones we know how to solve. So if you have, your nonlinear f of x u, we get A by doing partial f partial x, and B, this is exact, that shouldn't be a squiggly, and B is partial f partial u. And so you can linearize your nonlinear system locally in some, neighborhood and approximate it this way, right? Any questions about this? Cool. Who's done this stuff before? Good number. Okay, excellent. We're like maybe half, 2/3. That's good. If anyone needs, some like help with this kind of stuff, remedial stuff, I think we can definitely put together like a recitation section on like linear systems and background stuff like that. Okay, cool. So those are like basically all of the kinds of dynamics we will encounter and need to like know about. Mostly the nonlinear stuff. You need to know what like configuration, state are, and definitely the linear system stuff. We're going to spend a lot of time with those. Okay, cool. So we're going to kind of switch gears here and talk about some new concepts. So the next thing we got to know about are equilibria. So can anyone give me like an intuitive definition of an equilibrium point or equilibrium? Yeah, that's it. So like intuitively, what does that mean? Doesn't move. It's a place where the system can like stay at rest. So if you get it there, it's also a zero of the dynamics, right? X dot equals 0, so F equals 0, right? It's a place where the dynamics equals 0, which means if you can park it there, it's not going to move in theory, right? So this is, sort of obviously X dot equals F of X U equals 0. So algebraically, these are roots of the dynamics function. So unsurprisingly, we often end up using root finding algorithms to find these things on general nonlinear systems. So let's go back to our favorite nonlinear system. So if we write those dynamics down, we've got theta dot, and we've got minus G over L sine theta without the control. So just the regular pendulum. So this has to equal 0. So then we get, trivially, the top line gives us theta dot equals 0. What about the bottom line? So yeah, we get down here, theta equals 0 or pi, or really anything modulo pi, right? which is going back to this whole idea of the manifold's a circle that wraps around on itself, right? So there are really only two equilibria. There aren't an infinite number, right? Which is kind of this whole idea. It's so the fancy math way of saying that is the configuration manifold is compact. It just means it doesn't go out to infinity. It sort of wraps around on itself. Okay, cool. So yeah, the cartoony picture is, you know, hanging down, which we sort of obviously know, and then also straight up. Those are the two equilibria. Cool. Okay, so now we get to do our first control problem. So those are the two natural equilibria for the uncontrolled system. If I stick my control input in there, now I can mess around with it. So let's ask, can I move the equilibria around with my control input U? So sort of obviously the answer is yes, otherwise we wouldn't be talking about this. So let's try, what if I want to stick the equilibrium out sideways at like pi/2? How would I do that? So let's go back to our dynamics. So the top one's obvious, that just, you know, velocity has to be 0. Otherwise it would not be at rest. And I'm just going to go plug in pi/2 in the bottom line with the U now, which remember is the torque at that joint. So these guys both have to be 0. First one's easy. So let's go look at the bottom lines. That gives us the following. So we get 1/ml² equals g/L sine pi/2. Sine pi/2 is just 1. So this says U equals mgl. So if I take my motor torque and set it to mgl, now I've made that, I've gotten rid of the bottom equilibrium point and the top one incidentally, and now I only have this sideways hanging out equilibrium point. It's kind of an interesting thing. This is actually, has anyone heard of bifurcation theory? Bifurcations. This is sort of an example of this, where you can basically create and remove equilibrium points as a function of U in the dynamics. Yeah.
So that only work the initial state is
Yeah. So this whole equilibrium point idea is just that all it says is if you were to plug in that state,
okay.
it would stay there, right? It's not saying anything about how you get there, right? Okay, which is, we're going to get into in a sec, which is a whole separate thing. But yeah, so you could imagine, right? Like if I have no control input, there's these two equilibrium points. As I start cranking on the U, if I just fix it as a parameter in the dynamics model, right? I can actually like remove, create, destroy equilibria, right? You can imagine if I crank it up really high, so I have a super big torque that's bigger than, you know, mgl, now it's just going to spin around forever. And I've gotten rid of the equilibria entirely, right? So there's all kinds of weird stuff you can do here. Okay, cool. What was I going to say? Yeah, so in general, this is a root finding problem. And you can sort of ask questions like, if I wanted to make a particular equilibrium point exist, if I wanted to like make up a new one X star, I could, as long as I have enough control authority, as long as I have enough actuators, I can plug in X star and then solve a root finding problem in U to get f of X star comma U equals 0. And the U star that does that is the one I need. And I plug it in and I can make that equilibrium point happen, right? Kind of cool. So we get this problem, right? So I can plug in any X star I want and solve for the U such that this is true. And that's, you know, now I've made that X star an equilibrium point. You can't do this all the time. This depends on certain conditions, right? But yeah, sometimes you can do it. Okay, so any questions about equilibria? Places where you can park your system? Maybe. Okay, so now we get into the details of the whole parking statement. So intuitively, we talk about this pendulum, right? So this one we all know is stable. If I park it there, it's going to stay there. The one up here is not stable. If I park it there and I blow on it, it's going to fall over, right? Okay, so now we're going to talk about that idea, stability of equilibria. This is bread and butter control stuff. Usually when we talk about designing controllers, the implicit in that is stabilizing the system. We're usually trying to stabilize either an equilibrium point under disturbances that maybe originally was unstable. Good example is if I want a quad rotor to hover. Quad rotor hovering is unstable open loop. If I just put like, gravity compensation thrusts in there, it's like doing this and it'll blow over. You need active feedback control to stabilize that hover equilibrium. So the whole game there is basically figuring out what controller you need to make that thing stable in that open loop unstable, like naturally unstable equilibrium. So this is deeply tied up with things we like to do in control. Okay, so we're gonna go for like the simplest nonlinear dynamics kind of picture we can to think about this. So the intuitive idea is, when will we stay in the neighborhood of sort of near an equilibrium point under perturbations? So if I poke at the system, will it come back or blow up? So let's look at a 1D system. So here I don't mean like F equals ma in one dimension. I mean the state is one dimensional. So X is just in the real line. So in this situation, I can draw everything there is to know about the dynamics, which is kind of cool. So let's do that. So the x-axis here is the state x, and then the y-axis is x dot, or f of x. So I can draw a curve here that is f of x. This is the dynamics, right? In this simple like 2D plot. So I'm going to just make up an f of x, like sort of roughly looks like a cubic, say. And now, how many equilibria does this dynamics have? 3, right? All the zero crossings. So we'll circle those. And now let's look at each of these and think about what's going to happen under perturbations. So let's say we'll take the middle one first. So if I poke the system a little bit to the right, what's the sign on x dot? It's negative. So that means that the dynamics are going to push the system back towards the left. If I poke it to the left, x dot's positive. So the dynamics are going to push you back to the right. So there's this natural restoring force going on that's going to push you back. So this is stable, right? Under perturbations, the natural flow of the dynamics is going to push you back to the origin. So let's look at the one on the right. If I poke that to the right, x dot is positive. So the natural flow of the dynamics is going to push you farther away to the right. So that's going to blow up. So same thing the other way, right? If I push it to the left, dynamics are negative, it's going to go farther to left, right? And so the same picture holds on the left side as well. So the ones I did in red, these are unstable. And then this one in green is stable. Okay, so if I now think about this a little bit, I can write down a nice, clean mathematical condition for stability. So think about the one in the middle. What's the slope of f of x there? Negative. So this means partial f partial x being negative means you're stable. And then conversely, if that slope or derivative is positive, I'm unstable. Super intuitive, nice little cartoon picture. Turns out the generalization to like n dimensions is trivial. All you do is take, so now let's, okay, so in higher dimensions, now what is df dx? So if my state's in Rn, this is an n by n Jacobian matrix, right? And so anyone have a hint at what we're going to do here? Not singular values, but close. Not negative definite. So negative definite thing is if you have a symmetric quadratic form, right? That's where we talk about definiteness. So this is not a symmetric matrix in general. It's not a quadratic form either. Right? It's just a Jacobian. So what we're going to do here is take an eigen decomposition of this guy, which does what? It finds a coordinate transformation, the eigenvectors, right? An eigenbasis such that this matrix is now diagonal, which means in that particular coordinate frame or basis, you've decoupled the dynamics into a whole bunch of 1D systems. So now I can use the 1D, simple 1D result. And basically all of these conditions just get applied to the eigenvalues now, right? Which are all the decoupled 1D systems. Make sense? You got that? So that's it. Right. So then we just do the same thing. So it turns out what you want is the real parts of the eigenvalues of that Jacobian. All have to be negative for it to be stable. And so the idea there is, you know, even if like just one of the eigenvalues is positive, if you're starting out with a random state or you have any kind of noise, right? If you just pick a random initial vector, if you're choosing things randomly, some component of that initial state is gonna have some component along the unstable eigen vector, right? In which case that one's gonna blow up, and in a very short amount of time, that one's gonna end up dominating. So if any of the eigenvalues are positive, you're unstable. Okay, any questions about that? Jacobian eigendecomposition, check the eigenvalues. The real parts are all negative, you're stable. Otherwise, you're unstable. Easy enough. Okay, so let's do it on the pendulum. So we've got f of x is, yeah. No, strictly less than. Equals 0 is we're going to talk about right now, actually, because it's going to happen. Okay, so if I do the pendulum, so here's the pendulum dynamics. If I take the Jacobian, I get, you know, d derivative respect to the top row respect to theta 0, respect to theta dot is 1, bottom row respect to theta is minus g over L cos theta, and then 0. So that's the Jacobian. And now let's take partial f, partial x. Let's do the upright one because we know what that's going to be. So if I evaluate this guy at theta equals pi, I get 0, 1, cos is 1, so I get g over L, 0. And then if I take the eigenvalues of this guy, this is actually pretty easy to do by hand, but I'm not going to make you do remedial linear algebra. You get this guy, plus or minus square root g over L. So plus or minus, they're real, it's a pair of real guys, and one of them's positive. So you're unstable. So that's pretty clear. And now we're going to do the other one. So this is theta equals 0. So if we just evaluate that guy at theta equals 0, we get a sign flip over here. And then this guy has pure imaginary eigenvalues. So now it's plus minus I root G over L. So this has 0 real part, right? Does anyone know what this case? Yeah, so this means you have undamped oscillations. So here's the thing about this. In the linear setting, we call this marginally stable. And this basically means you're going to have undamped oscillations. But this is only in the linear approximation. So if you're doing this on a nonlinear system, if you've linearized a nonlinear system and gotten this result, all bets are off. Because what this says is that, you know, the linearization 0, the next order term in the Taylor series is then going to dominate. And that thing could do anything, and you just don't know, right? So this linearization thing, if it comes out with real part equals 0, all bets are off, and you have to do a nonlinear sort of fancier stability analysis. Does anyone know what that is in general? Lyapunov stuff. Yeah, so you have to look at a Lyapunov function, which you can easily do here on the pendulum. You just look at the energy, total energy, and you can show that that's bounded, and therefore this thing is stable, actually. But you can't get that from the linearization, so you got to be extra careful. So if I were to, though, on this system, add damping, which I could do, for example, through a controller by, say writing down u equals minus k theta dot, for example, that will give you a strictly negative real part in those eigenvalues from the damping. And then you would be stable. Okay. That was amazingly well timed. It's never that good. So that's it for today. Right on the money. I'll hang out for a little bit if anyone wants to chat, ask questions, etc. Yeah, thanks for coming out. See you Thursday.